Welcome to Lecture 3. This will be the last of our introductory lectures in which we will concentrate exclusively on linear algebra, but that doesn't mean we won't return to that topic in subsequent lectures if it's necessary. Now, you might recall that at the end of Lecture 2, in the problems, in fact, in my hint for the third problem on the second quiz, I challenged you to think about the following. I said something along the lines of find a basis for x which is equal to the set of all vectors in R3 such that x plus 2y plus 3z is equal to 0. And I gave you a hint which was that the dimension of x is equal to 2. And the reason that that is a useful thing to know is that it tells you how many vectors will be in the basis. Remember that that's always true. If you want to know the dimension for any space, that's simply equal to the number of vectors in any basis for that space. So in this case, we're looking for two vectors that will form a basis for x. In other words, we're looking for two vectors, let's call it v1 and v2, and these must have the property that any vector in x can be written in terms of those two vectors. In fact, let's write that down to make sure we're all together. So we want to find two vectors, v1 and v2, such that any vector in x could be expressed as a linear combination of v1 and v2. In other words, for any vector v in x, there must be some scalars, alpha and beta, such that v is equal to alpha v1 plus beta v2. Okay, so that's what we're looking for. And I don't know, maybe at first that seems like a somewhat daunting task, but it turns out to be very easy. In fact, and this is part of what, to me makes linear algebra very interesting. It's almost like magic in a way, because it turns out that we can pick any two vectors in x, and as long as they are not a multiple, as long as neither one of them is a multiple of the other one, then they will work. So let me show you what I mean here. So I'll pick as my first vector, I'll pick v1 is equal to 3, 0, negative 1. Now that's just an arbitrary pick. I will admit, though, that there's one thing I've done there, which you might want to do in situations like this as well, and that is, if you can, it's always useful to make at least one of the coordinates equal to 0. And so that's what I've done here, is I've made the y coordinate equal to 0, and so I get the vector 3, 0, negative 1. Now, I claim, I claim that if I pick any vector v2 in x, it will work as long as v2 is not a multiple of v1 and v1 is not a multiple of v2. Okay? So, keeping in the spirit of trying to make at least one of the components equal to 0, what we might do is say, well, let's pick v2 equal to 2, negative 1, 0. Notice that in v2, the z component is 0. And let me make sure you understand here exactly what I'm saying. How do I know that v1 and v2 are vectors in x? Well, because they satisfy the condition for x, which is that x plus 2y plus 3z is equal to 0. Notice that both of those vectors, v1 and v2, satisfy that condition, and furthermore, it's very clear that v1 is not a multiple of v2, v2 is not a multiple of v1. So I claim that the set consisting of those two vectors is a basis for x. And now let's try to verify that. Okay, and remember that the verification consists of two things. Show that any vector in x can be written as a linear combination of v1 and v2. That's one part. And then the second part is show that this set of vectors is minimal. In other words, if we took one of them away, then we could not write all the vectors in x in terms of the one remaining vector. But as long as we have both of them, then we can write all the vectors in x in terms of those two. Okay, so let's see how this will go. Well, let's pick a general XYZ vector in x. How do we express this vector in terms of v1 and v2? Well, let's see what happens. We have x, y, z is equal to alpha v1 plus beta v2. And what we want to show here is that we can find formulas for alpha and beta that will always make this work. So alpha times v1, well, v1 is 3, 0, negative 1, and v2 is 2, negative 1, 0. And therefore, we have 3 alpha plus 2 beta for the first component, minus beta for the second component, and minus alpha for the third component. And that vector here on the right-hand side must be equal to this vector over here on the left-hand side. And so you can see for those vectors to be equal to each other, each component must be the same. So we have x is equal to 3 alpha plus 2 beta, y is equal to minus beta, and z is minus alpha. And therefore, you see how our choice of making the y component of v1 equal to 0 and the z component of the second vector 0 has led to simple expressions here for the y and z component, which in turn has allowed us now to solve for alpha and beta very easily. We find that beta is equal to negative y and alpha is equal to negative z. And therefore, we already have the result that we had sought, and that is the vector xyz is equal to alpha, which is negative z, times 3, 0, negative 1, plus beta, which is negative y, times 2, negative 1, 0. This is the way that we can express any vector. This is how we can express any vector in X in terms of V1 and V2. Now that may seem like magic to you. Like I say, notice that we didn't think about the X component there at all, but it will surely work out. Let me show you what I mean. Let's look again at this equation. Remember that the equation for X, for the set X, is that it's all vectors here, such that the X component plus 2 times the Y component plus 3 times the Z component is 0. So let's come down here. Let's pick another arbitrary vector in X. Remember now, we must obey that the X component plus 2 times the Y component plus 3 times the Z component is equal to 0. But as long as we pick that, we're okay. So let's maybe pick, I'll pick Z is equal to 1 and Y is equal to 2. And so if we pick that, then this equation would say X plus 4 plus 3 is equal to 0. So that would mean that X is negative 7. And therefore, negative 7, 2, 1 is an element of x. And if we check that, we can see that it's certainly true, because if we check to see x plus 2y plus 3z, well, x is negative 7 plus 2 times 2 is 4. Negative 7 and 4 is negative 3. And then negative 3 plus 3 times 1 is positive 3. So negative 3 and positive 3 is indeed 0. So that verifies that this vector is indeed in x. And what I'm claiming, so I'm claiming with our formula up here, that vector, negative 7, 2, 1, must be equal to the negative of its z component, so that's negative 1, times the vector 3, 0, negative 1, and then minus its y component, so minus 2 times the vector 2, negative 1, 0. I claim that that's true because of this formula right here. Now, does it all work out? Well, let's see. Negative 1 times the first vector would give us negative 3, 0, positive 1. And then negative 2 times that second vector will give us negative 4, positive 2, 0. And now when we add these two vectors together, we get negative 7, negative 2, 1, sure enough. So like magic, this is all worked out. Now, of course, it's not really magic, and we can, I mean, if you're interested in knowing the inner workings of this a little bit better, you can see why it all works out in the following way. Now, what I've done is complete now. I have shown, before we move on, I want to make sure you understand, I have shown that any arbitrary vector, x, y, z, any vector in the subspace X can be expressed in terms of 3, 0, negative 1, and 2, negative 1, 0 by this formula right here. So this is for sure. I've shown that will work out. Maybe I need to show you. I'm still going to show you why the x component works out. It's clear why the z and the y components work out. I'll show you why the x component works out in just a moment. And as far as 3, 0, negative 1, and 2, negative 1, 0 being a minimal set is concerned, I think that's pretty clear, simply because these vectors are not multiples of each other. So if we had just one of them, if we took all the vectors that were a linear combination of one of them, we would just have a straight line. But when we take all linear combinations of both of them, we have a plane. And that is indeed what this set is. The set of all vectors who satisfy, or which satisfy this equation, is indeed a plane. Another way of saying, or another way of showing that if we took one of these away, it would not be, what would be left over would not be sufficient, is to say, well, if we took 2, negative 1, 0 away, we know 2, negative 1, 0 is a vector in X, but we can't express it as a linear combination of 3, 0, negative 1. So that shows 3, 0, negative 1 alone is not sufficient. And likewise, if we took 3, 0, negative 1 away, and we're left with just 2, negative 1, 0, that would not be sufficient, because the 3, 0, negative 1 is a vector in X, and it could not be expressed in terms of 2, negative 1, 0. So both of these vectors, or let's say two vectors that are in X, and neither of which is a multiple of the other, are needed, and these two will do. Now let's come back down here to this formula, and you can see a little bit better why it works out. Let's come down here. Okay, we have x, y, z is equal to negative z times 3, 0, negative 1, minus y times 2, negative 1, 0. Now, why is it that this formula works? Well, let's investigate. The first vector is the same as minus 3z, 0, z. And the second vector is the same as minus 2y, y, 0. Now, when we add these two vectors together, we get minus 2y minus 3z, y, z. Now, if you compare that vector, well, what we have on the left is clear that the second components do indeed match, and it's clear that the third components do indeed match. But what about those first components? We have x over here, and we have negative 2y minus 3z over here. So it doesn't look like those match. But keep in mind that this vector here was chosen to be an arbitrary vector in x. And what does that mean? Well, we can say since this vector is in x, we know that x plus 2y plus 3z must be 0, because that's how we choose our vectors in x. And what does that mean? That means that x is equal to minus 2y minus 3z. So we could plug that in right up there, and we see that this vector is indeed equal to x, y, z. So it's not, once we see that, the magic sort of disappears there, and we see why this all works out. So that's how we could find a basis for the vector space x. And once again, really it's very, very easy. All you have to do is to find any two vectors in x that satisfy this condition and such that neither is a multiple of the other. And that will do. Now, in the arbitrary case, it would be a little more difficult than that, because keep in mind, I did help you out by telling you the dimension of this was 2. In general, if you were just given some arbitrary subspace, then and you wanted to find a basis, then the first thing you might try to do is to find its dimension. And why would you want to find that out? Because then you would know how many vectors you're looking for. But let's say that you were working in some large subspace, and let's say you wanted to find a basis, and somehow you figured out the dimension was 7. Then what would happen? Well, you'd have some equations describing, just like you have this one equation, which would give you the conditions for vectors in x. Well, you would have some equation, or possibly multiple equations in that case, describing the vectors in this 7-dimensional subspace, and you would simply have to find 7 vectors that satisfy those conditions, and such that none of them could be written in terms of the other 6. Now, of course, that could be quite a task, and you don't have to worry. We're not going to be doing anything like that in this course, but that would be the idea. So maybe before we move on, we should look at one more example of this. Let's say maybe find a basis for x plus 2y minus z equals 0. Oh, I'm sorry, this is an equation here. What I want to say is find a basis for x equals set of all x, y, z in R3 such that x plus 2y minus z equals 0. So try to do this. You stop the video now. Try to do it on your own, and then I'll do it myself. But keep in mind that there's not a unique answer here. So even if we come up with different answers, that doesn't mean that either of us is wrong. But stop the video now. I encourage you to stop the video, and then after you think you have a good answer, let's come back and look at it together. Okay. So what I would do here is, again, I want to pick V1 and V2, and as usual, I'll try to pick them in such a way that some components are 0. So I'll pick V1 equal to 1, 0, 1, and I'll pick V2 equal to 0, 1, 2. Now clearly V1 satisfies this condition. V2 satisfies this condition. So V1 and V2 are clearly in X, and neither is a multiple of the other. And by the way, I'm telling you again, I'll give you the hint, which you might have already figured out since it's so similar to the previous example, that the dimension of this X is also 2. So I claim that this is a basis. And again, to verify it, okay, we'll pick X, Y, Z in X and show how to express it in terms of V1 and V2. Okay? So we'll have X, Y, Z is equal to alpha V1 plus beta V2, which is alpha times 1, 0, 1 plus beta times 0, 1, 2, which is alpha 0 alpha plus 0 beta 2 beta, which is alpha beta alpha plus 2 beta. And now again, we want this vector to be equal to the vector on the left. And so that tells us immediately that alpha must be chosen to be equal to X, and beta must be chosen to be equal to Y. And I claim that if we will make that choice, everything will work out. So let's see. Okay, so X, Y, Z, I'm claiming is equal to X times 101 plus Y times 0, 1, 2. This is I claim that this is the way that we can express any vector in the subspace X in terms of the vectors v1, which is 1, 0, 1, and v2, which is 0, 1, 2. And so now I simply want to verify to you that it will work out. Well, x times 1, 0, 1 is x, 0, x. And y times 0, 1, 2 is 0, y, 2y. And so when we add those together, we get x, y, x plus 2y. And so clearly we see that the first component works out. Clearly we see that the second component works out. But what about this third component? We have z on the left-hand side. We have x plus 2y on the right-hand side. But remember now, this vector x, y, z was chosen to be a vector in x. And for all vectors in x, x plus 2y minus z is 0. X plus 2y minus z is 0, which implies that z, if we keep z on one side and take the x and 2y over to the other, z is equal to x plus 2y. And there we have it, because here is x plus 2y, and so indeed this is equal to x, y, z. And so therefore any arbitrary vector x, y, z in the space X can be expressed in this way in terms of our vectors v1 and v2. And furthermore, v1 and v2, neither one of those can be expressed as a multiple of the other. So v1 and v2 do constitute a basis for this space X. And that's it. That's the ideas may be new to some of you, but I think it's after you look at it, you see it's a fairly straightforward idea. And so now let's investigate another property, and that property will be called orthogonality. Before we talk about orthogonality, we need to introduce the idea of a dot product or inner product. So let's proceed in this way. Let's suppose that V1 well, here. We'll suppose V1 and V2 are elements of Rn. And what this means is that each one is a vector with n components, n real components. So, for instance, we would have V1 is equal to x 1, 1, x 1, 2, x 1, 3, dot, 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 down to x 1, n. That might be the components of V1, and V2 could be x 2, 1, x 2, 2, x 2, 3, dot, 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 down to x 2n. And the dot product of V1 and V2 is, I'll put a delta over it to mean that this is defined to be equal to x11 times x21 plus x12 times x22 plus dot 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 plus x1n times x2n. So you just multiply the first components together, the second components together, the third components together, and so on, and then add up all of those products, and you get, in the total will be the dot product or inner product of V1 and V2. And this is an idea that I imagine that all of you have seen before, but still we can look at a couple of quick examples. If perhaps we're looking at R3 and we had that V1 is equal to perhaps 1, 2, 3, and V2 is the vector 4, 5, 6, then V1 dot V2 is equal to 1 times 4 plus 2 times 5 plus 3 times 6, which is equal to 4 plus 10 plus 18, and that is equal to 32. Now, the reason that we have a dot product is it has some interesting properties. One is that the dot product allows us to calculate the length of a vector. Let's suppose that, well, let's look at the example that we just had. The length, this symbol, now in some books you'll see just one bar, and rather than these double bars used on each side, in some books you'll see just one bar. But I like to use 2 bars to distinguish this from absolute value. Of course, you don't take the absolute value of a vector, but sometimes it can be helpful just to have the double bars to remind you that that V in this case is, or V1 in this case is, a vector. Anyway, the magnitude or length of a vector, length of V1, it's also called the magnitude of V1, and it is equal to the square root of V1 dotted with itself. So in this case, for the V1 that we have here, it would be the square root of 1 times 1 plus 2 times 2 plus 3 times 3, or 1 times 1 is 1, and 4 is 5, and 9 is 14. And similarly, the magnitude of V2 in this particular case would be the square root of 4 times 4 plus 5 times 5 plus 6 times 6, which would be 16, and 25 is 41, and 36 is square root 77. So the dot product, or the inner product, gives us a way to calculate the length of a vector. And then another important concept about the dot product is the following. V1 dotted with V2 is equal to the magnitude of V1 times the magnitude of V2 times the cosine of the angle between them. So, for instance, if these are the two vectors V1 and V2, and they are, notice their tails are connected here, then we call this angle theta, and the relationship between the cosine of that angle and the lengths of the vectors and the dot product of the two vectors is given by this equation, which is rather important. And notice that this could be manipulated into this form. And so now we are finally ready to talk about orthogonality. V1 and V2 are said to be orthogonal to each other if V1 dot V2 is equal to 0. And so in the present case, that would mean in this present case, orthogonality means exactly the same thing as perpendicularity. The two vectors are perpendicular to each other, and we can see that because if we can see that here from this equation, if v1 dot v2 is 0, then that means the cosine of the angle between the vectors is 0, which would mean that the angle is 90 degrees. So that's what we will mean by orthogonality of two vectors, is that their inner product is 0. And let's ask, why are we interested in orthogonality? Well, one reason for being interested in orthogonality is the following idea. Let's suppose that, well, let's just keep this simple and let's say, note that 1, 0 well, let me maybe start over in a different way. Okay, let's read this now. So if we, this is an example now. We're trying to understand why we're interested in orthogonality. And so the example is as follows. We have a vector v1, which is 1, 0, and another vector v2, which is 0, 1. And I claim that those two vectors taken together form a basis for R2. Now that's the first part of what I'm claiming, and I think that that's very clear. We've talked about that before, but any vector in R2 could be written as alpha times this first vector plus beta times the second vector. That's clear. For instance, the vector, let's pick a vector in R2. Let's say maybe 5, 7. Well, 5, 7 is equal to 5v1 plus 7v2. So clearly, any vector in R2 could be written as a linear combination of those two vectors. But furthermore, in addition to that, this basis has the property that the vectors in it are orthogonal to each other. Now, why is that useful? Well, in order to understand why it's useful, I need to get another basis in which that's not true, and then you can see which one is more convenient to use. So let's come up with another basis. I'll say, note that if V1 equals 1, 1, and V2 equals 2, negative 7, then V1, actually, let me call these V3 and V4. So that's V3 and V4. Then V3, V4 is a basis for R2, and that this basis consists of vectors that are not orthogonal to each other. Now, I'll show in a moment that this really is a basis. In other words, I'll show that any vector in R2 can be written as a linear combination of V3 and V4. And it's clear that any basis of R2, we've already said R2 is two-dimensional, so any basis must have two vectors. So we couldn't get by with less than two vectors, so we must have V3 and V4 both. But so I'll show that part in a moment, that this really is a basis. Now, the part that these vectors are not orthogonal to each other is easy, because if we take the dot product of V3 and V4, what do we get? 1 times 2 is 2, plus 1 times negative 7 is negative 7, 2 and negative 7 is negative 5. So the dot product of V3 and V4 is not equal to 0, it's equal to negative 5. And therefore these vectors are not orthogonal to each other. So now the question is, why might one prefer the first basis over the second one? And an answer is, it is much easier to express an arbitrary vector in terms of orthogonal vectors than it is to express one in terms of non-orthogonal vectors. And let's see that that's true. So I'll take an arbitrary, I'll say demonstration. Suppose that we wanted to express 7, 11 well, of course this is not an arbitrary vector, but you get the point. This is a specific vector. But express 711 in terms, well, I'll say first in terms of V1 and V2, and then in terms of V3 and V4. Okay? Well, in terms of V1 and V2, nothing could be easier. 711 is equal to 7 times 1, 0, plus 11 times 0, 1, which is 7V1 plus 11V2. But what if we want to express 711 in terms of V3 and V4? Well, we get 711 is equal to alpha times 1, 1 plus beta times 2, -7. And so this would be alpha plus 2 beta and alpha minus 7 beta. And so we end up having to solve this system of equations. 7 is equal to alpha plus 2 beta, and 11 is equal to alpha minus 7 beta. And admittedly, I mean, it's not too hard to solve that system of equations, but this is a lot more work finding the coefficients in this case than it was in this case. Now, you might be saying, well, that's not a really good comparison because these two vectors have the advantage, V1 and V2 have the advantage that each one has one component equal to 0. But let me show you that even if that were not the case, it would still be easy to find the coefficients as long as the vectors and the basis are orthogonal to each other. So let's look at another, one more example. Note that V5, which is equal to 1 over square root of 2, 1 over square root of 2, and V6, which is equal to 1 over square root of 2 minus 1 over square root of 2, is another basis. Well, I'm sorry, let me rephrase this a little bit. I'll say, note that if V5 equals 1 over square root of 2, 1 over square root of 2, and V6 is equal to 1 over square root of 2 minus 1 over square root of 2, then V5, V6 is a basis for R2 consisting of orthogonal vectors. Now we will see how easy it is to express the 711 in terms of these vectors. So we just found above that it was very easy to express 711 in terms of 1, 0, and 0, 1, but rather tedious to express 711 in terms of the non-orthogonal vectors 1, 1, and 2, -7. But let me show you now that as long as we pick two orthogonal vectors, it's always going to be easy. It doesn't have to, we don't have to have vectors with 0 components. It will always be easy as long as the vectors we choose are mutually orthogonal. And let's see why that's true. Okay, so we have 7, 11 is equal to alpha times 1 over square root of 2, 1 over square root of 2, plus beta times 1 over square root of 2 minus 1 over square root of 2. Or we could also write alpha v1 plus beta v2. Now, instead of expanding this and getting a system of equations as before, we're going to do something smarter. We're going to say, we're going to take the dot product of each side of this equation with v1. Now remember, these two vectors, oh, and I'm sorry, that shouldn't be v1 and v2, but v5 and v6 here. So v5, v6, v5, and v6. Okay? Now, notice that, as we said, v5 and v6 are orthogonal to each other. In other words, if we take the dot product of v5 with v6, we get 0. And you can see that 1 over square root of 2 times 1 over square root of 2 is 1 half. 1 over square root of 2 times minus 1 over square root of 2 is minus 1 half. 1 half minus 1 half is 0. So that means that when we come down here and try to express the vector 7, 11 in terms of v5 and v6, okay, we get alpha v5 plus beta v6, but then if we take the dot product of both sides of v5, this term right here, since v6 dotted with v5 is 0, that will disappear, and we just get alpha times v5 dot v5, or alpha times the length of v5 squared. So that means that implies that alpha is equal to 7, 11, it's equal to 7, 11 dotted with v5 over v5 dot v5. And similarly, beta would be equal to 7, 11 dot v6 over v6 dot v6. And both of these we can compute very quickly. 7, 11 dotted with v5 would be 7 times the square root of 2 plus 11 times the square root of 2. So that's 18. I said times the square root of 2, I meant over the square root of 2. So that's 18 over the square root of 2. And then in the bottom, v5 dotted with v5 is 1 over square root of 2 times 1 over square root of 2. So that's 1 half plus 1 over square root of 2 times 1 over square root of 2 is 1 half. So it's just 1. And for beta, 7 times 1 over square root of 2 is 7 over square root of 2 minus 11. So we have minus 4 over square root of 2. And v6 dot v6 happens to be 1 as well. And so we're done. Alpha is 18 over the square root of 2, and beta is minus 4 over the square root of 2. And notice that we didn't have to solve any system of equations at all. We got immediate formulas for the coefficients alpha and beta, and that happened simply because when we use this expression and then dotted each side of the equation with either v5 or v6, when we dot each side with v6, this term dropped out. On the other hand, if we had dotted, that's when we dot each side with v5. On the other hand, if we had dotted each side with v6, then this would be v6 dot v5, this would be v6 dot v6, and so we get this equation. So when you have a basis consisting of orthogonal vectors, it makes it much easier to express some arbitrary vector in terms of those basis vectors. And we will see in the book that we're almost always going to be working with bases that do consist of orthogonal vectors. And in fact, not only orthogonal, but orthonormal vectors, which means that the vectors are all orthogonal to each other and all of them have a length of 1. That was the case here in this last example. Notice that v5.v5 was 1, v6.v6 was 1, and this made it even more convenient to work with. So that's a brief introduction to the ideas of orthogonality, and also a continuation. We wrap up the notion of a basis. So now let's look at problems for this video. Okay, so our problems will be as follows. For 3.1, we're given a subspace which consists of all vectors in R3 that satisfy x plus 2y plus 3z is equal to 0. And you want to circle each of the following that is an orthonormal basis for x. Now, just to review, the orthonormal basis means it's not only a basis for x, but also the vectors in the basis are orthogonal to each other, and they have a length, each of them has a length of 1. So here are your choices for A, B, C, and D. And I believe all that's clear, but I'll just read it quickly. So for A, the two vectors are 3 over square root of 10, 0, minus 1 over square root of 10, 1 over square root of 35, minus 5 over the square root of 35, 3 over square root of 35. For B, it's 3 over square root of 10, 0, minus 1 over square root of 10, 2 over square root of 5, minus 1 over square root of 5, 0. For C, it's 3 over square root of 10, 0, minus 1 over square root of 10, 1 over square root of 35, minus 5 over the square root of 35, this is a 5, and 3 over the square root of 35, and 0, 0, 0. And finally for D, 2 over square root of 5, minus 1 over square root of 5, 0, 3 over square root of 70, 6 over the square root of 70, and minus 5 over the square root of 70. So identify all of those that are orthonormal bases for x. Number 3.2, what is the angle between 1, 2 and 2, 1? And you have the choices 36.87 degrees, 45 degrees, 20 degrees, 90 degrees, and 3.3 will be given in class. And that concludes both this video and our introduction to linear algebra. And so on our next video, we will begin working on problems in our book. So good luck.